In the name of Almighty God, I'm Mahsa Zankoshi, and today I want to talk about multibody dynamics in contour multiphysics simulation software. Today I want to go through the theory for joint forces and moments computation. The joint forces and moments are evaluated in the global spatial coordinate system as well as in a joint local coordinate system. The joint forces and moments are referred to the center of joint in the current position. For the joint that have translational degrees of freedom, the center of joint should be interpreted as fixed to the source side. Now I want to go through the summing reaction. Forces over the boundaries. This is the default method for computing the joint forces and moments when flexible domains are attached to the joint. The computation can be done on either the source or destination attachment. The convention is that the force and moments are the ones acting on the attachments from the joints. The sign changes if you switch between using the source or destination attachment for the evaluation. This joint forces is computed by integrating, that is, a summation over all nodes the reaction forces on the attached boundaries. For example, we have F is equal to sigma, the lower boundary is I, the upper boundary is nodes Fi. The joint moments are computed first by integrating the cross product of reaction forces and position vector of each node relative to the centroid of the attachment boundaries and then transferring it to the center of the joint. For example, we have a MR is equal to which is indicating to the MA attachment is equal to sigma lower boundaries I upper boundaries nodes RR XI minus XR multiplied by FR and M is equal to MR or M attachment plus XR plus UR minus XC plus UC source multiplied by F. Here the subscript R indicates that the centroid of attachment and C indicates the center of joint. Ri is the rotation matrix representing the rotation of the attachment and U represents the displacement. Now I want to go through the using weak constraints. When using weak constraints, the joint constraints are applied in a weak form and the values of the Lagrangian multipliers give the joint forces Fw and moments MW. This works for both flexible and rigid components. The use of Lagrange multipliers can, however, have an effect on the structure of the equation system which limits the solver that can be used. The joint forces and moments are computed as F is equal to Fw, M is equal to Mw, plus USC destination minus USC source multiplied by Fw. The correction term of the moment appears in joints that have translational degrees of freedom because Mw is computed on the destination attachment, which can have moved relative to the source attachment. The sign convention in this case is that the forces and moments should be interpreted as acting on the destination attachment. Now I want to go through the using penalty formulation. When using penalty method, the joint constraints are applied using a penalty formulation and the values of the penalty forces FFP and moments MAP give the joint forces and moments. This works for both flexible and rigid components. Moreover, this also works for over-constrained rigid body systems in which the weak constraints method might not work due to an insufficient number of equations for the Lagrange multipliers. Since the value of penalty factor directly affects the joint constraints, it should be chosen judiciously. The penalty factor value should be large enough to ensure that the joint constraints are not violated by beyond a permissible limit. At the same time, the penalty factor should not be too high, since that will make the system of equations numerically ill-conditioned. The penalty forces FAP and moments MAP are computed as FAP is equal to PJ multiplied by CAU. MAP is equal to 0.1 d to the power of 2 PJ multiplied by C theta, where CAU and C theta are translation and rotational violations of the joint constraints respectively. The penalty factor PJ is the input having a default value 0.1 d equilibrium. In this expression, equilibrium is the effective Young's modulus, and D is the geometrical diagonal of the bounding box of the geometry. The computation of joint forces and moments using penalty forces and moments is as described above. For the weak constraints method, F is equal to FAP, M is equal to MIP plus USC destination minus USC source multiplied by FAP. Now I want to go to the camp follower theory. In this section, we want to go to the camp follower, closed point determination, camp with boundary selection, camp with edge selection, camp follower connection force computation theory for friction in camp follower. The first chapter is camp. A camp is defined through a set of boundaries or edges that is being followed by a point called follower. The camp section can be defined on rigid as well as on elastic bodies. Thus, camp boundaries or edges can undergo any kind of rigid body motion as well as deformation. When defining a camp selection, it should be also possible to use boundaries or edges that are defined outside the physics interface. Now I want to go to the follower. A follower is defined to a point that follows the camp boundaries or edges with certain option offset. The following options are supported to define a follower point: a centroid of selected entities, domains, boundaries, edges, or points, geometric point, single point. The follower point can be a part of rigid or elastic bodies in case there is a requirement of multiple points to follow the camp boundaries or edges. Multiple instances of these features should be used. Now I want to go through the closed point determination. A general extrusion operator is defined in order to find a point on the cam boundaries or edge that is closer to the follower point. The general extrusion operator used has the following settings: source selection, cam boundaries or edge destination map, special position of the follower point, source frame, special frame, mesh search method, closed point. Now I want to go to the cam with boundary selection. Figure 3-1 illustrates example of a cam follower with a cam having boundary selection. Connection constraints section. The following constraint is added in order to impose the cam and follower connection. Gap is equal to 0 in the case the connection is conditionally active. The constraint expression is modified to the following: gap multiplied by slip is less than delta is equal to 0. Here delta is the connection tolerance. The gap and slip variables used in the connection constraints are defined in the following section. Gap and slip the definition. The gap variable is a measure of distance between the follower point and its closest point on cam boundaries in the special normal direction. The slip variable is a measure of distance between the follower point and its closest point on cam boundaries. Hence, it is used to activate or deactivate connection constraints based on the specified connection tolerance. The gap and slip between the follower point and cam boundaries can be defined as: gap is equal to xf minus xc multiplied by nsc minus x offset. Slip is equal to absolute xf minus xc minus x offset. Here xf is the spatial position of the follower point, xc is the spatial position of a closed point and the cam boundaries, nsc is the spatial number of a closed point on the cam boundaries. X offset is the initial offset gap between the follower point and the cam boundaries in the normal direction. Now I want to go to the cam with edge selection. Figure 2 dash Figure 3-2 illustrates example of cam follower with a cam having edge selection. Now I want to go to the connection constraint. The following constraint is added in order to impose the cam and follower connection. Gap is equal to 0 in case the connection is conditionally active. The constraint expression is modified to the following: gap multiplied by slip is less or equal than the delta is equal to 0. The here delta is the connection tolerance, the gap and slip. Using the connection constraint or define the following section. Now I want to go through the gap and slip definition. The gap variable is a measure of displacement vector between the follower point and its closest point on the cam boundary. The slip variable is a measure of distance between the follower point and its closest point on the cam boundary in a special tangent direction. Hence, it is used to activate or deactivate connection constraint based on the specified connection tolerance. The gap analysis between the follower point and the gap cam edge can be defined as gap is equal to xf minus xc minus x offset minus sleep multiplied by t 1c. X offset is equal to rsc multiplied by x offset minus x offset multiplied by t Tennessee multiplied by t Tennessee. Sleep is equal to xf minus xc multiplied by t minus c. Here, xf is the special position of the follower point. Xc is the special position of the closest point on the cab edge. T1c is a special tangent of a closest point on the cab edge. X offset is the initial offset or gap vector between the follower point and the cam edge. Tennessee is the material tangent of the closest point on the cam edge. RC is the rotation matrix of the cam. Now I'm going to go through the cam follower connection force computation. The cam follower connection constraints can can be imposed in several forms. The first is point-wise constraint, weak constraint penalty method. The connection constraint enforces a continuous contact between the cam and the follower. However, in order to find out whether the follower remains continuously in contact with the cam, the connection force can be computed. The negative value of the connection force throughout the rotational cam indicates the continuous contact between the cam and follower. The point-wise constraint is the default form of the cam-follower connection constraints. In this form of constraints, the reaction forces representing the connection forces are not computed. In order to find connection forces, weak constraints or a penalty method can be used. Now I want to go through the using weak constraints. When using weak constraints, the connection constraints are applied in a weak form, and the values of the Lagrange multipliers give the connection forces F(W). The use of the Lagrange multipliers can, however, have an effect on the structure of the equation system, which limits the solvers that can be used. Now I want to go through the using penalty formulation. When using penalty method, the connection constants are applied using penalty formulation, and the values of the penalty forces FAP give the connection forces. Since the value of penalty factor directly affect the connection constraints, it should be chosen judiciously. The penalty factor values should be large enough to ensure that the connection constraints are not violated beyond the permissible limit. At the same time, the penalty factor should not be too high because that will make the system equations numerically ill-conditioned. The penalty forces FAP are computed as FAP is equal to PSC multiplied by gap, where PSC is the penalty factor input having a default value 0.1. The equilibrium in this expression, A equilibrium is the effective Young's modulus and D is the geometric diagonal of the bounding box of the geometry. Now I want to go through the theory of friction in cam follower. A friction subnode described under friction cam follower is used to add frictional forces and losses to a cam follower. The friction force is modeled using a continuous friction law capable of modeling sliding and sticking phenomena. A strict application of Columbus law involves a discrete transition from sticking or to sliding, and vice versa, as dictated by a vanishing relative velocity. A discrete transition can cause numerical difficulties. To avoid it, the friction force is approximated by continuous friction law. The magnitude of the friction force is calculated by this formulation. FAF is equal to minimum micro F plus FAR and FA max multiplied by 1 minus e to the power of minus velocity slip as absolute divided by nu zero. Here F is the constant force, FAR is the additional sliding resistance, FA max is the maximum friction force, and V slip is the slip velocity vector, and nu zero is the characteristic slip velocity. The term is 1 minus e to the power of minus absolute velocity slip divided by nu zero is called the regularization factor. The regularization factor smooths the friction force discontinuity. The characteristic slip velocity should be small compared to the characteristic relative velocities encountered during the simulation. The continuous friction law describes both sliding and sticking behavior, and it replaces Columbus law. Sticking is replaced by creeping between the contacting bodies with a small relative velocity below the characteristic slip velocity. The normal force at the contact point can be taken as a computed connection force. The friction factor force vector is defined as FF is equal to FF velocity s divided by absolute velocity s, where FF is the magnitude of friction force. Now I want to go through the energy dissipation rate. The energy dissipation rate due to friction at the contact point is defined as QF is equal to FF multiplied by velocity s. Now I want to go through the gear theory. In this section, we want to go through spare gear theory, helical gear theory, bevel gear theory, bore gear theory, spool rack theory, helical rack theory. Sport gear theory. The sport gear theory is defined as a rigid body. A finite stiffness for the gear mesh or the gear tooth can be specified in the gear pair node while connecting to other gears similar to the rigid domain, and the spare gear is a material model which is mutually exclusive to all other material models. The only material property needed is the mass density. Figure 3-3 illustrates a sketch of an external spare gear showing the two's cross-section and various parameters such as center of rotation, gear axis, pitch radius, and pressure angle. Figure 3-4 illustrates a sketch of an internal spare gear showing the two's cross-section and various parameters such as the center of rotation, gear axis, pitch radius, and pressure angle. For details about the theory of rigid bodies, see the rigid material section in the Structural Mechanics Module User's Guide. Connection to other gears. A spare gear can be connected to the following gear types: another spare gear or a helical gear to the gear pair node, a worm gear through the worm and wheel node, a spare rack or a helical rack through the rack and pinion node. A single gear can be connected to one or more gears. Mounting methods. The motion of a spare gear can be constrained directly using its subnode. Alternatively, it can be mounted on a shaft. There are several ways through which a gear can be mounted on a shaft. Some of commonly used methods are as follows. For example, directly mounted on a flexible shaft, mounted on the rigid or flexible shaft through a rigid or elastic fixed joint, mounted on a rigid or flexible shaft through a rigid or elastic hinge joint, mounted on a rack ground, a fixed shaft through a rigid or elastic hinge joint. Center of rotation. Gears are defined to rigid body degrees of freedom. These degrees of freedom are created at the center of rotation, and the rotation is interpreted about this point. By default, the center of rotation is set to the center of mass, but there are other ways to define it explicitly. This is the point where you interpret the forces and moments that act on the gear due to meshing with other gears. Gear axis. The gear axis is the axis of rotation of the gear that passes through the center of rotation. This axis is used to create the gear's local coordinate system in the gear pair node. The gear rotation, a degree of freedom in the gear pair node, is also interpreted about this axis. Gear properties. The following quantities are required to define a spare gear: number of teeth, pitch, diameter, DMP, pressure, angle, alpha. The transverse module of the gear is defined as MT is equal to DMP divided by M. The normal module of the gear is defined as MN is equal to MT. Now I want to go through the helical gear theory. The helical gear theory model is defined as a rigid body, a finished stiffness for the gear mesh or a gear tooth can be specified in the gear pair node while connected to the other gears. Similar to the rigid domain, the helical gear is a material model which is mutually exclusive to all other material models. The only material property needed is the mass density. Figure 3-5 illustrates a sketch of an external helical gear showing the two's cross-section and various parameters such as center of rotation, gear axis, pitch radius, gear pressure angle, and helix angle. Figure 3-6 illustrates a sketch of an internal helical gear showing the teeth cross-section and various parameters such as center of rotation, gear axis, pitch radius, pressure angle, and helix angle. For detail about the theory of the rigid body, see the rigid material section in the structural mechanics module user's guide. The following section is an addition to the spare gear theory section, which is also applicable for the helical gear. Now I want to go through the gear properties. The additional parameter helix angle beta is required to define a helical gear. The positive helix angle is interpreted as right-handed and negative helix angle is interpreted as the left-handed. The normal module of the gear is defined as Mn is equal to Mt cosinus beta. Bevel gear theory. Bevel gear theory model is defined as a rigid body. A finished stiffness for the gear mesh or gear tooth can be specified in the gear pair node while connected to the other gear. Similar to the rigid domain, the bevel gear is a material model which is mutually exclusive to all other material methods. The only material property needed is the mass density. Figure 3-7 illustrates a sketch of a bevel gear showing the gear cross-section and various parameters such as center of rotation, gear axis, pitch diameter, and con angle. For detail about the theory of rigid body, see the rigid body material in the structural mechanics module user's guide. The following sections is an addition to the spare gear theory section, some of which is also applicable for the bevel gear. Connection to other gears. A bevel gear can be connected to another bevel gear through the gear pair node. A single gear can be connected to one or more gears. Gear properties. The additional parameter cone angle gamma is required to define a bevel gear. The positive cone angle results in a decrease in diameter along the gear axis. Worm gear theory. The worm gear model is defined as a rigid body of stiffness for the gear mesh. A gear pull tooth can be specified in the worm and wheel node while connecting to a wheel similar to the rigid domain. The worm gear is a material model which is mutually exclusive to all other material models. The only material property needed is the mass density. Figure 3-8 illustrates a sketch of a worm gear showing the tooth cross-section and various parameters such as center of rotation, gear axis, pitch radius, pressure angle, and lead angle. For details about the theory of a rigid body, see the rigid material section in the structural mechanics module user's guide. The following section is an addition to the spare gear theory section, some of which is also applicable for the gear theory. Connection to other gear. A worm gear can be connected to a helical gear and a spare gear to the worm and wheel node. A single gear can be connected to one or more gears. Gear properties. The following quantities are required on define a worm gear: number of stars, n, Pitch diameter is dp, and pressure angle is alpha. Lead angle is phi, and handness right or left. The helix angle for the right-handed worm gear is defined as beta is equal to p divided by 2 minus phi. The helix angle for the left-handed worm gear is defined as beta is equal to minus p divided by 2 minus phi. The transverse module of the gear is defined as mt is equal to dp divided by n. The normal module of the gear is defined as the mn is equal to mt cosine beta. Thank you so much for watching my tutorial video until the end. Today is the 10th of the June 2026. Time is 3 in AM. Also, you can download the appropriate, proper, and related console multiphysics simulation file from my github.com/masterscript.